Hey everyone, in this video we will have a brief introduction to multivariable functions and level curves. So one question you might ask is, why do we need multivariable functions? Why do we care about multivariable calculus? And the reason is there are many real-world applications. So we've already seen just in our class, right, like volume of a cylinder, area of a triangle. These are things that rely on two different inputs to determine their output. We have just often fixed one of these variables so that we could perform single variable calculus, but it's often useful to obviously let both of these variables change. In economics, right? So I mean, profit, I guess, is just a function of these two variables, right? It's revenue minus cost, but there's a lot more that goes into each of those respectively, right? You're thinking about labor, you're thinking about production, advertising, all of these different things that factor in. Something a bit harder to define, at least for an actual function, would be rather complicated, but a person's happiness, right? If you're like most people I know, then there are quite a bit of different things that contribute to your happiness or unhappiness. And then lastly, statistics. Well, last on this list, but absolutely not the last overall application. But yeah, things like PER in the NBA or, WAR. These are like comprehensive statistics that try to analyze how good a player is, and they have a lot of different things that go into them, right? So PER is going to have rebounds, assists, points, field goal percentage. All of these things go into a single function. So multivariable function is just one that is going to have more than one input. So, f of x, y, x, y, z here. We have two variables, three variables here. In variables, kind of showing you that you can have as many variables as you want, and then you'll have an output that depends upon these, right? And so this first one is one we'll look at a little bit more in depth, but all three of these guys are perfectly fine multivariable functions. So the graphs of these things, now the last two are pretty much impossible, but if you have two variables, we can still draw those pretty well. So if you think about one variable, right, we draw that in the plane because we just have one independent, one dependent. So as x changes, y changes, you can draw it using just two axes. But if you have, say, z equals f of x, y, then here you have this third variable introduced that depends on the other two, right? So you need like a third coordinate. And so in this case, you're drawing in the x, y, z, like three-dimensional space. And so I'll just draw quickly like x squared plus y squared. So this is what's called paraboloid, and it basically looks like a 3D bowl shape sitting on the origin. And I will now show you a better picture of this. Right, so this is a much better and easier to see version. And so your origin would be down here, and then our up direction is z here, and then you have x and y being perpendicular in the other two directions. Now, you may say to yourself that it's not very obvious to me that x squared plus y squared is going to give me something that looks like this in 3 dimensions. And that's very fair. But we have a way, if you struggle to visualize things in 3 dimensions, to actually use 2 dimensions to get a good picture of what's going to go on. And this is what's called level curves. So let's think more about this. What are the cross sections here, right? If I just take a line across and I go through really more like a sheet of paper through it, and I just look at a cross section horizontally, it's going to be a circle, right? All of these are kind of circles that are expanding and getting wider as I go up higher. So let's see this more symbolically. All right, so let's consider this more carefully. So z equals x squared plus y squared, and this is what's called a paraboloid, by the way. So first note that z is always going to be non-negative, right? Because we're squaring x and we're squaring y and we're adding them. So there's no way we could get a negative number out of this. And so what I want you to do is think of these cross sections. Well, how do you get a cross section? You're fixing a height, right? And so if you think of z as vertical, this is really fixing a z value above the xy plane, right? And so, if I start by just z equals 0, well, what do I get here? I get x squared plus y squared is 0, which means that x and y are both 0. And so I get like the point, the origin in the xy plane. Okay, well, what if I have z equals 1? Well, then I get x squared plus y squared is 1. And I know what this is. This is the unit circle. And I notice in general, right, x squared plus y squared is a circle of radius r if I have it equal to r squared. And so, I'm going to go up to my next perfect square here, z equals 4. This gives me a circle of radius 2. And you can keep going, right? So like z equals 9 gives me a circle of radius 3. And then 16 for 4, and so on. And so I can draw this all in the xy plane as long as I label it. And so this picture in the xy plane shows you exactly what's going on, right? So I get these circles as my cross sections, and I've just kind of labeled them going out, and I'm saying, okay, so I started at z equals 0. As I go up to 1 vertically, I've gone out to the circle of radius 1. I go up again by 3 to z equals 4. At height 4, I have the circle of radius 2 in blue here. And then lastly, I go up to height 9 above the xy plane, and it looks like this. So basically, you want to think of looking from above, right? You're basically looking down from the heavens, if you will, and you kind of see this bowl shape, the paraboloid, as this flat surface, and you just kind of see how the cross sections look as if they were smashed down on the ground. And so without ever drawing the three-dimensional thing, you can kind of see what's going on. You just have these circles that are getting bigger and bigger as you go up, and so you naturally form that bowl shape. And that lets you draw a three-dimensional thing by only looking in 2 dimensions. So for your first exercise, I want you to kind of think about what we just did and try to draw the level curves for this similarly defined function, right? We still have the x squared plus y squared, but we're now taking the square root of it. So draw a few level curves from 0 to 3. Again, z is always going to be non-negative here. And then I want you to use those level curves to try to figure out what does the 3D graph look like in this case. So let's look at one more example. So here we have z equals x plus y. So this is what's called linear, right? Because we see only powers 1 of x and y and nothing higher. So like the previous one, that paraboloid was a quadratic multivariable function. So you saw squareds showing up. But this isn't just a line, even though it's called linear. This is not a line. And here, since we can, let's go ahead and see what happens when z is negative 1. Right, we didn't have any level curves that were negative last time. So if we have negative 1 equals x plus y, which is very possible, right, then y is negative x minus 1. And we'll graph these here in a second. So I'll set up 4 different points. If z is 0, then we get y is minus x. If z is 1, then we get y is negative x plus 1. And notice that all of these are lines of slope negative 1 in the plane, right? And then z equals 2, say, then we get y equals negative x plus 2. So these are all slope negative 1, and it's just different vertical asymptotes, right? And so this first one goes through negative 1, has slope negative 1. Next one goes through the origin, slope negative 1. Next guy goes through 1, and they're all parallel to each other. And it looks something like this, right? And of course, these would extend forever in each direction. So, this goes up with positive z, and these ones are negative z. And so what is the shape that we get here? So what's our 3D shape? So again, these are different heights, but we just get lines. So this is a plane, but it's not it's not parallel to the xy plane, right? So this is like a slanted plane in 3 space. And the reason we know it's not parallel to the xy plane is if it were, then it would all be at the same height, right? So you'd only have one level curve, and we definitely don't see that here. It's changing height throughout. And for your second exercise, I want you to find the level curves for this function, the absolute value of x plus the absolute value of y. Again, for like 0, 1, 2, and 3, this one, again, can only have non-negative values of z. And then try to describe what you think the 3D graph looks like based off of those level curves. Thank you for watching.